Hello and welcome to Physics 2212 Lab 2, Lines of Charge. Today we're going to be going over the purpose, introduction, concepts and background, preliminary results, assumptions/environment, our glow script code, which will make up the majority of our time here, and some discussion questions at the very end. So the purpose of this lab, which is outlined in the lab instruction, is to produce a computational model of two charge tapes exerting an electric force on each other, and use this model to estimate the amount of charge on each tape necessary to float one above the other. So in other words, create hovering tape calculations. Pretty self-explanatory, basically the last lab, but more accurately. So here's some very important laws we need to understand. Newton's second law, sum of force equals mass times acceleration. That's very important to understand when dealing with the gravity and equating that to our electric force. Newton's third law, every action has an equal and opposite reaction, just pretty important to remember. Electric field of a point charge, pretty familiar with that guy. Electric force is just the charge times that electric field at that position. And superposition is adding up all those fields together to get a net one. So, our preliminary results states from lab 1 that our charge was Q equals 1.3138 e to the negative 8 coulombs. However, if we look through the actual thing, we are 238% off versus the point charge versus the line charge module, and we have 3.11594 e to the negative 8 to actually cause the tape to float. So let's kind of figure out why that's the case. Some assumptions before we get fully into it though. We have our ignoring air resistance, pretty important, we do that for most physics. We assume each tape has the same charge, just for the sake of equating things and making our computations actually possible. We assume that the charge is evenly distributed across the tape, so that way you can break it up into equal segments, which is what the next assumption is. Assuming that we can segment it into equal segments, so that it's actually possible to do that kind of thing. The total charge on each tape is the sum of the charges of the segments. So, basically just, we're making sure the dq dl thing actually works. So let's get into the code, which is the meat of our stuff. So we can see here that we have our Python code. Now, of course, we got to set some things at the beginning. So we got our constants like k, our proton charge, our electron charge, which is the negative of that, atom length, etc., g. This is a lot of the stuff from the first lab. Our measurements is just, the width of the tape, tape length, some mass of it, all those things, and a distance. So pretty standard things. And then the net charge, which is 1.3138 e to the negative 8 times that little percentage thing, just to kind of help show it on a more visual level when we actually get the model. So E field is all these things, so basically just a point charge formula, but then that's kind of like defining it, if that makes sense. And then we get the line of charge, which is a similar thing. We're just doing for II in range n, dq is etc. Right? So it's for that radius and position of those things. Pretty cool. So superposition, this is just a for loop right here. And you can see it's basically just finding each charge, each point, and then for looping it so you can do it again and again and again, so you can get that net electric field kind of thing. And of course, up here is the object creation stuff as well. And when you put all that together, you get this really cool model right here. So let's kind of delve a little bit into what's going on here. So the green is the force of acceleration and gravity acting upon this red tape. Pretty important to understand. And since they perfectly cancel out in our approximations, that this yellow charge is the perfect opposite of that with the electric force from the difference in charge here. Or the equality in charge here, right? Pretty cool. So we can see here in orange is kind of the main meat of this lab, right? What's going on? So we're splitting up the charge into tiny, tiny pieces and then equating the force at that point specifically based off of that kind of assumed net equal spread on the tape. Obviously, that's not the case normally, but for this, we're just going to assume it is. And the red and blue is just the tip. So they kind of shoot up into the air at different points. You can see it's not the same equally like we assumed in the first lab. And the results, basically what we said before, it's 238% of the original guy, and it's 3.11594 e to the 8. So there's some possible error. Mainly our measurements from lab 1 are inaccurate, or the coding from lab 1 is incorrect. That would cause POE and cause the whole thing here to not be accurate at all. Let's get into these discussion questions. So what if we had modeled our tapes as a single point charge, like in the previous lab? Well, let's just compare our charges then. We have 1.3138 e to the negative 8 and 3.11594 e to the negative 8. So I guess the next question is, well, why are these different, right? Well, which value is close to the real value? So these estimates differ as a point charge is widely egregious for an approximation to make something as large as a tape, which, as calculated in the last lab, was composed of well over a couple billion atoms. Therefore, the line charge model is likely far more accurate, as it accounts for the surface of the entire tape, as opposed to simply assuming it was a charge. So it's accurate because it's actually accounting for the fact that it's tape and not a charge, if that makes sense. Yeah. Thank you for watching, and I hope you have a good day.